Marco Fedi. Space. A dilatant fluid. What physical characteristics does 95% of the universe, the dark universe, possess? Two proofs have been given that space behaves as a shear thickening fluid. As a dilatant fluid. Let's use the Lorentz factor in Stokes' equation, as the factor of space's apparent viscosity. Stokes' equation. For a body traveling through a Newtonian fluid, it expresses the viscous force acting against the direction of its motion. The variables are its radius, its speed, the viscosity coefficient of the fluid. Let's now prove that the Lorentz factor is space's apparent viscosity coefficient, in the following form. In this case, space is a non-Newtonian fluid, because the coefficient of apparent viscosity is nonlinear. The asymptote is justified by the fact that bodies accelerated to relativistic speed cause dilatant space to enter a transient and local solid-like state, due to the very high shear stress. Through this solid-like dark medium, transverse waves at very high frequencies are possible. We call them photons, and they propagate at the highest speed in the universe. Resorting to the Lorentz factor, as an apparent viscosity factor, let's write a modified Stokes equation expressing the viscous force exerted by space on bodies that travel in a vacuum. The new equation refers to vacuum's viscous force, the viscous force of free space. And we see that the Lorentz factor is used as the coefficient of apparent viscosity of the vacuum. We see a constant whose value is 1 and it doesn't affect the calculations. Since space probes travel in a vacuum, let's use this equation of vacuum's viscous force to directly calculate the Pioneer anomaly. The anomalous deceleration of the Pioneer probes measured by the NASA. -8.74 times 10 to the -10 meters per square second. To calculate the acceleration, let's use Newton's law F equals ma. Using the viscous force of the vacuum in the numerator and the mass of the Pioneer 10 in the denominator, we obtain the Pioneer anomalous acceleration. Let's write in full the equation of vacuum's viscous force. We see the antenna radius equal to 1.371 meters. Initial mass minus burnt hydrazine equal to 222 kilograms. Maximum speed reached during the Jupiter flyby, equal to 36,737 meters per second. The exact value of the anomaly is thus obtained and is the most accurate result ever achieved for the Pioneer anomaly. So what about the current thermal solution, which until now has been considered the correct solution in the absence of a more precise and convincing solution? Turashev's 2012 thermal results are not as accurate, because they are based on simulations, on partly uncertain data, and contain a large margin of error. Space viscosity expressed by Stokes' equation, modified with the Lorentz factor, is therefore the most direct and precise solution to the Pioneer anomaly. We can say that the dark substance that corresponds to 95% of the universe interacts with space probes. Hence it also interacts with the planets, causing the perihelion precession. Most evident for Mercury. The dimensionless form of Fedi's equation is used, omitting the radius, treating Mercury as a point mass, as is also the case in general relativity. We see that in a few steps, starting from this non-dimensional form of the equation of space's viscous force, resorting to Taylor and to the elliptic parameter, we obtain an equation expressing the precession in a semi-orbit, and then the equation for the complete precession of the perihelion, that is, of the part of it exceeding what is foreseen by classical physics, thus obtaining a value that is in accordance with general relativity. Since the relativistic precession of Mercury's perihelion was the first classical test of general relativity, and the same result can now be obtained in a flat and viscous space, we can reasonably assume that Einstein's curved spacetime can be replaced with pressure gradients in a fluid dilatant space, moving from geometry to a more strictly physical approach, and from a non-quantum approach to a field where we can easily define a quantum potential. Diplanetary orbits decay due to the viscosity of space. The larger the mass of a body, the weaker its acceleration. Planets are much more massive than space probes. Orbital decay due to space viscosity is negligible over trillions of years. Resorting to Fedi's equation for the Earth, it is equal to only -9.92 times 10 to the -26 meters per square second. Same thing for pulsars. They are too massive to be perceptibly slowed down even in trillions of years.